Hi, I'm Tina Green.
And I'm Lexi Mossman.
Here's our video of the biomechanics involved in tennis. Wow, what a great serve. We all know that Serena is one of the best in the game, so who better to help us out with our project? The first topic that we will be learning about are free body diagrams. To begin, we are going to construct a free body diagram of Serena's serving arm right before she contacts the ball. Looking at this will give us a better understanding of the arm position just prior to contact. For our free body diagram, we will be ignoring air resistance. We will first construct the stick figure diagram of Serena's serving arm. This is the shoulder joint. Now we can begin to add the forces. The first force that we will always include is the force of the weight of the object. We will call this Fw. Fw is composed of the weight of the arm multiplied by the force of gravity. Fw always acts at the center of mass of the object. The next force that we will include is the force of the racket. We will call this force Fr. Fr is composed of the weight of the racket multiplied by gravity as well. As you can see, both of these forces will be acting down on the arm. The next force that we will include is the force from the muscle. This force we will call Fm, and it will be acting back towards the joint to keep the arm in full extension right before the serve. Finally, we will include the joint reaction force. This force is comprised of a force acting in both the x and y directions. After we have included the joint reaction forces, we are done with our first free body diagram for the arm right before Serena contacts the ball.
Wow, what a great shot. Wouldn't it be cool to know just how far over the net the ball goes? Using projectile motion, we can find the height of the ball. Let's first list what we already know. It is given to us that the horizontal distance the ball traveled is 15 meters. And the time it took for the ball to travel that distance is 1.8 seconds. Now we can use the projectile motion equations to solve for the distance in the y direction that the ball traveled. The first equation we will use is Vf equals Vi plus At. Let's use this information so that it correlates to the y direction. We are going to be solving for VIY. We will assume that the ball lands and has a zero final velocity, which equals VIY plus the gravity, negative 9.8, and the time that we were given, its peak. The next equation we will use is change in x equals Vi in the x direction times t plus 1/2 at squared. Because there's no acceleration in the x direction, we can say that this portion equals 0. We already know that the distance traveled is 15 meters. We'll be solving for Vix, and the time we know is 1.8 seconds. So we can say the velocity in the x direction equals 8.3 meters per second. Using this information, we are now able to find the time at the peak. We can find this by using the change in the x equals the Vix that we just solved times t plus 1/2 at squared. But this time we'll be using the distance and the time as it correlates to the peak. So we can say that 7.5 equals 8.3. We're solving for time plus 0 because this is the x direction. So time at the peak equals 0.9 seconds. Squared plus 2a delta y. This is 0, as we know, because the final velocity at the peak will be 0, equals the initial velocity that we solved, which is 17.6 squared, plus 2 times gravity times the change in height. We now know that the change in height that the ball traveled is 15.8 meters.
I wonder what caused that ball to drop so quickly. The last component that we will be looking at is called Magnus force. Magnus force is a lift force of tremendous importance to many athletes who want to bend the flight of the ball. Magnus force is the reason that ball dropped. But just how does that occur?
The surface of the tennis ball moves air next to its surface as it rotates. This is called surface drag. Because the ball is rotating, the surface area creates an area of high velocity and low pressure, and an area of low velocity and high pressure on the other side of the ball. In the case of our drop shot, the area of low pressure will be on the top side of the tennis ball. The difference in the air velocities creates a pressure differential between the front and the back of the tennis ball. As the ball moves, a pocket of high pressure is created in the front of it, and with the lift that is created, the ball drops back toward the area of low pressure behind it, causing the ball to drop quickly.